Well, I'd like to thank Sanji for inviting me, and happy birthday to Red, and happy birthday to the Field Robotics Centre. So I thought I'd put the sun and the surf on the first overhead and then get on with the automation. You can see largely why I live in Australia and not Pittsburgh. Also I feel the need as the only overseas speaker here to align another coordinate frame for you. This is effectively where Australia sits. It's essentially in the middle of nowhere. It's very large, about the size of the US, and it has relatively few people in it, fortunately. And it's an ideal place to do field robotics for those exact reasons. So field robotics, not just in my group, but other people in CSIRO, for example, have been pursuing field robotics now for probably longer than a decade, 15 years at least. And there are lots of great applications in Australia, whether it's in areas, commercial areas like mining, agriculture, but also offshore airborne systems, cargo handling, you name it. Basically, field robotics is a good thing to do in Australia. So let me tell you about a few of the things we've been doing. And the way I thought I'd flavour this was actually to pick out what I think are the three pearls of wisdom I have got to in the last 10 years. Okay? The first of these is integrity. And some of you call it reliability. We don't think about reliability, we think about things will fail, how are we going to detect that and recover from it and deal with it, all right? And that's so much important to many of our projects. The other thing that we've learned over the years is there's an awful lot of systems engineering in building field robotics. And it would be nice if there was a science of systems engineering that you could actually reuse from one project to the next. And I think we've got a little bits of that there. And the third thing is perception. The environments you work in, it's an exciting place to work because every environment you go to is different. All right? And that really means tackling the perception problem head on. No straight lines, not even any curves in most places. So the way I thought I'd do this is I'd pick up on a couple of my favourite projects and just kind of show you the kinds of lessons we learned out of these. And I'm going to pick up on one which I think is probably familiar to most people here, which is the automated cargo handling system. And in that project we learned an awful lot about how to build things that never fail. All right, that have to operate 24 hours a day, 365 days a year without a PhD student within 1,000 kilometres. All right, and that's a sort of measure that you really want out of it. And also the systems engineering lessons we learnt out of it. And then somewhat chronologically, I'm going to say a little bit about some of the distributed data fusion work that we've been doing. Again, because we've got to worry a lot about how you design extremely complex systems, field them and guarantee that they will work first time. All right? There is no forgiving when you come to things like UAVs. And in particular, there are lots of issues associated with how you actually merge and put together sensor information. Then, it's a great talk earlier. I'm going to talk a little bit about our work in underwater vehicles, and particularly the perception problem as it relates to things like SLAM and so on. Because it's been a real eye-opener for us that with some fairly basic technology, you can really do some very good, or you can help the scientists do some really good science. And I think this is something that we should learn in field robotics. It's good to attach ourselves to those kind of projects. And finally, something which I think is one of the big challenges for us in Australia is mine automation. There are lots of mines in Australia. They're having a lot of trouble manning them. There are a lot of issues with safety, predictability and so on. And certainly in the last 3 to 4 years, there's been a lot of interest in basically how we'd go about automating these things. And it really tackles all of these three issues head on. How we build a very robust system that always works, how we design a very large-scale system, and how we deal with all the sensor data that comes from that. So I'm kind of going to step through these and try and pull out these pearls. So I guess some of you are familiar with this, but it's the project I'm still most proud of, and the reason is I have nothing to do with it anymore. And it's a good project where you can actually say that. So we've got now 3 terminals in Australia that are completely unmanned, 35 straddle carriers in total. And in fact, the technical team live about 1,000 kilometres away from where this terminal actually works. It's been in commercial operation now for 3 to nearly 4 years, and it operates all year, all day, everything else. So it really has all those components that go and make it up. Admittedly, it's a simple world, it's blocks world, but it's still, you have to learn those lessons about how you make things work all the time, how you worry about systems engineering, all these kinds of things that need to go into it. So it's recently, in fact, in the last couple of months, it's actually set productivity records for a straddle terminal anywhere in the world. Okay, so this just shows you what you can do with things like this. And we've learned a lot of very valuable lessons. I wrote up a little paper not so long ago that carries many of those, but I'm really just going to focus in on these 2 things of building integrity and the systems design that goes into these. So perhaps one of our largest problems with building something like this is the fact that, when you're done with it, it can never fail. These are 60-ton machines doing 30 kilometers an hour. They have to work 24 hours a day, except for refueling, 365 days a year, and no intervention whatsoever. So you've got to basically guarantee that if things do go wrong with the machine, then you have to be able to detect that and recover from it. And we did some work a number of years ago. In fact, Steve Shedding, who worked here as a postdoc, did this for his PhD, in actually designing navigation systems in particular that would guarantee that we'd actually be able to detect any failure and recover from that single failure. All right? So that if something did go wrong, and typically in these sorts of devices it's a perception failure, so it depends on the weather, it depends on lots of things that you'll have never seen before. It's these unknown failures that really kill you in this kind of application. So to be able to guarantee that you can detect those is very important. And we designed some fairly simple guidance systems that had dual redundant loops. So here you can see a GPS INS loop, a radar encoder loop. We used a number of frequency domain ideas to model all potential faults in these kinds of systems, and then through the use of an information filter actually mix this information together so you're guaranteed to use the best data and actually discover when things actually go wrong. So this was a very valuable lesson for us, how to go about designing things like this and being able to hand it off to a client at the end of the day and say, that's it, we can walk away. So we've recently restarted, in fact, some of this work, and I thought I'd insert this slide just to show you the sorts of things that we're looking at now, which is to worry a lot more about how you build integrity into much more general perception systems. And we've got an interesting little project at the moment, in fact, that takes basically an interesting mixture of sensors, camera, IR, multispectral, millimeter wave, ultra-wideband radar, various different lasers, and you can see set up controlled environment conditions with different levels of dust, smoke, rain, and all these things, and actually generate a complete calibrated set of data that allows us to understand what sensors work in different environments and so on, and how we can detect failure, perceptual failure, in all these different types of sensors under what sort of conditions and so on. So this is going to be a very interesting result out of it. In fact, the data's already been generated, and in fact this entire data set will be made public for everyone to basically use this to look at this kind of information, to try and actually really study the problem of how you build perception systems that will last for long, long periods of time. So the other big thing that we looked at in the Straddle program was the systems engineering component. And we learned a very important lesson in this, and I put up an older AGV that I worked on up there. I think one thing that we didn't understand in the early days was people didn't want a robot. What they wanted was a system, all right, that did the job. And whether it had a robot or not in it was to a large degree irrelevant. And it was a big lesson to learn that what we needed to generate was not an autonomous vehicle, but an autonomous system. And that really means not just designing the vehicle and worrying about how the vehicle itself actually worked and drove, but actually in complete thing, how you then take, say, 35 of these things, put them all together, worry about cranes, other interactions, and so on and so forth, so that you can guarantee, again, whatever happens in the system, you're not going to collide, you're not going to destroy anything else that happens to be in there, and so on, and that it actually works effectively in terms of the overall system. Because ultimately, that's where the end user gets his payoff. All right? It's not just using a robot and removing one person, it's actually integrating an entire system. And I think we also got from that there are some key research issues that we had to face in field robotics, which is how you basically capture and abstract the operation, say, of a single vehicle, all right, and how you compose all that so you can actually make guarantees not about one vehicle anymore, but make guarantees about the performance of the overall system, its safety, its integrity, everything else that goes along with it. So this was one of the driving issues in some later projects, and I'm going to talk about them here. We've been doing a whole series of UAV projects over the last 10 years or more, which basically involve testing an algorithm, which I'm not going to go into a lot of detail about, called DDF, or Distributed Data Fusion. And DDF, basically, I'll explain in a minute a little bit, allows you to fuse information from a number of different platforms without having a central place where you actually put the information together. So we had a series of projects flying many UAVs together, with each UAV with multiple sensors on, each UAV able to talk to all the other UAVs so that you can actually put this information together, and ultimately to control the UAVs to actually gather that information.